All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you have all had an excellent weekend. I hope that you are all staying warm. In my office right now, like I've set the thermostat to be 23 or 24 or something, but it's just like 19. And it's making me, like my hands are just freezing cold this morning in my office. Yeah, welcome back to winter. Welcome back to winter. I really hate winter. I'm looking so forward for winter to be over, and I really want summer back. But now I'm just complaining about winter. Let's talk about operating systems. So, by the end of today's lecture, what I would like you to be able to do is describe how an operating system manages processes. So we started this last week. We ran a couple of processes on my system because I couldn't figure out how to get this to work on Aviary. And the backstory for that is that I had to ask the tech support staff to help me figure out why is this not working, because what I was doing should work. It should work. And they told me to look in certain configuration files that would have been in my user directory. And so I looked at those configuration files. These are not configuration files I ever edited. These are just something that I inherited by having an account created for me. And one of them explicitly turns it off, and I believe that this was changed in 1990. But I'm stuck here with this setting that doesn't make any sense for me to want to do this. So I figured that out mostly, but I would like to still spend a little bit of time taking a look at this today. The specific thing that I want to think about today in terms of processes is going to be a little bit more about the kind of metadata that our operating system is keeping track of about these running programs, but then also trying to get some sense of what this address space looks like. Address spaces are something that you would have seen in Comp 2280 for the first time. So this idea of code at the top, and then beneath that a heap structure, and then at the very bottom of memory is where your stack lives. This is a structure that you would have seen before, but we'll revisit it again. We're not going to dwell on it because we will be dwelling on it much later in the course. Today it's just to get a sense of what this thing looks like and what it's there for. Once we do that, I'd like to move on to describing the data structures that are used to represent files and directories as seen in Unix. And this is in two different ways that I want us to be thinking about this. The first way is literally the abstraction of folders and directories. What does this idea look like? How do you interact with these folders and files from a user perspective? So looking at the API of I call open and then I call read and that sort of thing. But then also things like this idea of an open file table. So what do I need to maintain as an operating system so I can call open, and so that I can call read, and so that I can call lseek and close and that sort of thing. Then the other half of this is, what does the file system's data structures actually look like? So how am I taking this data from a file and laying it onto a disk? How am I taking these bits and putting them onto a disk? What does that structure actually look like? I want to be able to think about this from all of these different levels. We're going to start this today. We're not going to finish it, but we're going to start it. We're going to be looking at describe how a specific file system is implemented, and I want to spend a little bit of time reviewing this idea of vsfs that's in our chapter and try to illuminate some of the parts of this structure that vsfs is. So pointing at things that I think the textbook doesn't do a great job of describing, and trying to elaborate on what that description is. So the thing in my mind specifically that the textbook lacks a little bit of is a further description of what this idea of direct and indirect pointers are for blocks. What does that structure actually look like in terms of the file system layout? The other half of describing how a specific file system implemented is show how common file operations are performed in terms of manipulating file systems data structures. All three of these different points are kind of interrelated with each other. So which data structures or which parts of the file system are going to be changed or used when I open a file? Which are going to be changed or used or read when I read a file? Which are going to be changed or used or read when I write to a file or create a new file in my file system? Which of the data structures are going to be used for that? So we're going to start that. Overall, we're going to be looking at two different file systems. VSFS is one of them, and the other one is exFAT. And like I said last week, exFAT is a real actual file system. VSFS is like for learning purposes. exFAT is the real deal. This is an actual file system that's used for realsies on real computers. You can format a drive as exFAT in Windows. This is a real thing that we're going to be taking a look at. So what I'd like to do is just quickly remind us of this idea of processes and continue to think about this idea of what are we asking the operating system to do and what kinds of things does the OS need to keep track of to be able to do this for us. So I've got this code up in my terminal. This is that same process code that we were looking at last week. I've already made this. There's a program here that's called print. I've already run make, so I'm just going to start running this. Remember that all this does is it just prints out the same character forever. There's a loop, and it's just looping and doing put char that character, and then put char new line, and then put char that character, and put char new line, and just going to sleep. One of the programs that we looked at last time was this PS program, and PS allows us to inspect the currently running processes on the system. Last week, what I said about this idea of program and process is that a program here, print, is this inert file. It's an inert file that's just sitting there on your disk. What I'm asking my operating system to do when I type this is, please take this file and start running it. Start running this thing. So when I say print-a -C with the letter B here, I'm saying, please start running this program. That's going to create a new process. And when I do PSA here, what we're going to see is that this one here is currently running. And what does the OS need to keep track of to be able to do this for us? There's a couple of things that we can see in this output. One of them here is PID. This is an identifier. This is a unique identifier for each process that happens to be running on the system right now. Every process that's running has a unique identifier. So this is the way that our OS is able to kind of distinguish between two different processes on the system at any given time. There's this thing that's called TTY. We're going to ignore that. This idea of TTY is like going back to the late 19th century and starting to think about teletypes, which is like, you know, typewriters sending messages across wires. We're going to ignore that. That idea still exists. It's there, but we're just going to pretend that it doesn't exist for now. This column here says stat. It means status. What is the current status or state of this running process? So when I do PSA, what it says right now is that this print-CA is S+. If I take a look at the manual page for PS, I'm going to zoom in here, and I'm going to press enter, and I'm going to search for state. These are the different state codes that PS prints out about the currently running processes. So we've got uninterruptible sleep, we have idle kernel thread, running or runnable, interruptible sleep, stopped by job control signal, stopped by debugger, paging, dead or defunct, zombie process. We will see these ideas again later, but what I do want to show you right now is if I do PSA here, and then I press Control-Z on my keyboard over here and run PSA again, suddenly the state of that process has changed in its output. Where it used to be S+, now it's T. T says that your shell has interrupted this thing, it stopped it. If I run BG, that's going to send this thing to the background, and now we're in state S. So our operating system is keeping track of each of these processes, each of these programs that are currently running on my system. It gives them unique IDs. It's giving them a state. It's also keeping track here of how long that thing has been running, but not like literal wall time here, but how much time it's been spending on the processor. So there's some additional extra stuff that's accounting for what's going on with this thing right now. The last thing that I want to see, and I'm not even going to draw this out because it's not important for our discussion right now, is I want to take a look at that proc file system just one more time. So I'm going to go to proc, and then what I'm going to do is I'm going to go to the folder that has this ID on it. Proc is this folder structure that lets you interact with the processes that are running on a Linux system, but they're just files. So you can inspect information about the running process by reading these files that are in this folder structure. So I'm going to change to this directory, and I'm going to zoom in here, and I'm going to open up this file again that's called maps. I'm going to just zoom out here on my shell so that this all fits all on one line. I realize that this is quite small, but again, the point is not to actually see what's here, but to get a sense of where everything is laid out. On the very left side of this output here these are the smallest addresses that are represented in this file. So this maps file tells me what the address space is for this particular process. At the very top, I've got the file in memory right now. So this is the name of the program file that's currently running in the process that I've got. If I change the name of this file, then it's going to be a different file name here that will show up in that part of memory. Beneath that, I have the heap. When we call malloc, this is where in memory all of our data is going when we call malloc. Beneath that, there's some other stuff that we're just going to pretend is not there right now. There's a bunch of stuff that's happening here related to the standard library that is kind of irrelevant for us. We'll think about it later when we talk about virtual memory, but for now we can just pretend, we'll just close our eyes, we'll just block it like this. We can't see that thing right now. Beneath that is the stack, and this is very close to the bottom of our address space. So if 0 KB is at the top, then whatever size of memory I have is close to the bottom, and that's where my stack is. And then again, there's some more stuff that's after this that we're just going to shut our eyes and pretend it doesn't exist. At an abstract level, we've got code, heap, and then stack on the bottom. And then importantly, all of these address spaces are isolated from each other for every process on the system. My print program cannot change something about another running process by writing to memory locations. It's not able to do that. Every process has its own address space. We will spend a ton of time talking about this whole idea later. For now, every process has its own address space. You don't have to worry about clobbering or changing or interrupting some other program when you write your program. When you get a seg fault, for example, it doesn't cause other programs to stop working. It's just your own program that stops working. All right, this is kind of the end of processes for us right now. We're going to come back, but yeah, any questions? Yeah. So that's a great question. When I hit Control Z on my keyboard right now and stop it, all the memory that this process has allocated, all the structures that our OS is keeping track of and metadata, it's all still there. Just nothing's happening. No instructions are currently being executed in that thing. When I do BG, what it's kind of saying is start it up again. Start running instructions in this thing and just keep going with whatever state it happened to be in before you suspended it in the first place. Yeah. We're not sending anything away until I do FG and then I hit Control C. Control C now says stop this process. When I ask the operating system to stop this process, I'm actually saying, please clean up everything about this process. Whatever memory you allocated for it, whatever other structures you allocated for it, get rid of them now. That was a good question though. Any other questions? Yeah.
So in the map file that you opened,
yeah.
I'm just wondering, so
yes, I can. Although it's gone now because I killed this process. So I'll start again. And I'm going to do PSA, and then I'm going to change directory into this, this number here right now.
Does that number change every time you start the process again? Does it give you a new unique versus
Every time you start a process, it's going to give you another different unique ID. They can be reused, like once you terminate a process and you start a new one, it's possible for that identifier to be reused, but they are unique as far as you're concerned. Yeah.
So I'm just wondering, the top part that has the file, why does that get printed multiple times?
So there's one other column that I, again, kind of just overlooked here, which is this one right here. And it has this structure R, and then W, and then X. And then there's a P in all of these. Each of these are going to be loaded into different locations in memory, and some of them will be readable, and some of them will be executable. Again, I kind of have to defer this to later because we're going to talk a lot about this. But the idea is that some parts of your program need to be readable, some parts need to be executable, some need to be both, almost none of them need to be writable. And you won't see any W's in the column that have that file there. Yeah. Okay? All right, cool. Any other questions? All right. Okay, awesome. We will revisit these ideas. We are going to come back to them. We will revisit these ideas, but for now, we're going to leave this behind. And I'm going to kill this program, even though it's not really doing anything. I don't want it to be eating at my battery while I'm sitting here at the front of the class. My stupid laptop only has 2 USB ports that I can actually plug things into. There are 3 USB ports, and there's a feature on this laptop where I can plug a USB cable into it and it becomes a display for another device, which is cool, I guess, but I can't put power into that USB port. And I've got a webcam here, and I've got the HDMI cable plugged into one of these USB ports, and it's dumb. It's really dumb. I need to buy like a hub or something. All right, so processes, we'll come back to this. The idea of address spaces, we'll come back to this, but for now, we're going to leave this behind. Let's start talking about file systems. So there are many, many different kinds of file systems. Computers and computing have been around for a long time. It's been around like since the 40s or 50s in the 20th century. Computers and computing have been around for a long time. This idea of permanent storage has been around for a really long time. There's this YouTube channel that I like to watch, and I admittedly spend probably too much time watching this YouTube channel that's called Usagi Electric. And this is someone that is getting old vacuum tube computers up and running again. And the permanent storage device for this thing is it's a magnetic drum that literally is a drum that is spinning like this. This idea of permanent storage has been around, and this is a machine from the 1950s. This has been around for a long time. With the march of time, with people, with different kinds of things, there are many different kinds of file systems that have shown up over the years. I'm going to give you a whirlwind tour of some of the common file systems that we might see today, but I want to be clear that I'm not really looking for you to be able to tell me anything about these file systems. I'm going to tell you a bunch of stuff because I want to use this idea of different file systems to motivate something. So first, there is this idea of these ext family of file systems. ext2, then 3, then 4 are all common Linux file systems. ext2 is the earliest one that was around like in the mid-90s basically, that it got merged into the Linux kernel and then was used on disks for that. ext3 adds support for something called journaling, which we're going to talk about in a couple of weeks. And then ext4 adds support for something called extents, which is referred to in the chapters that you were looking at for the textbook, but we don't really need to know too much about that. All of these file systems are open source. They're free and public and open source. Anybody is able to look at the source code for these things and use them as they see fit. A lot of common systems have ext for Linux for their file system. In fact, a lot of phones are using ext if you have an Android device. There's the FAT family of file systems. FAT here stands for File Allocation Table. FAT came from Microsoft. So when Microsoft was making DOS, DOS is a very early operating system. So when you're thinking about like Old computers, you'll see like text interface and nothing else on it. This is a DOS, a disk operating system. And all it really is like you can change directories and you can run programs, but it's completely within that terminal structure. You don't actually see any other kind of visual structure. This family of file systems kind of comes from that. FAT had limitations like there were no directories. It was just one big directory that had files in it and nothing else. You couldn't make directories. And then FAT12 came along and added things like making support for bigger files and also this cool feature of directories. And then FAT16 and 32 came along and gave you bigger file support than you had before. So you could make a bigger file than you could on just FAT. FAT had limitations like, I believe, don't cite me on this, but the limitations were like megabyte size files. FAT32 has limitations of like 4 gigabyte size files, but then we kind of get stuck there. So exFAT comes along and says, okay, well now we're going to make files addressable up to some huge size, like gigabytes and terabytes and petabytes. There's also NTFS. FAT12, FAT16, FAT32, and then exFAT. These are all Microsoft file systems that predate NTFS. NTFS is a file system that shows up with the Windows NT operating system, which is, again, kind of in the mid to late 90s. This file system adds cool support for things like, again, this idea of journaling, which we're going to see later, but it gives you, make sure that if your file system crashes, then you're not going to necessarily lose data that you might have otherwise lost. APFS is the modern Apple file system. Before this, Apple used a file system that was called HFS and then HFS Plus. APFS does a lot of cool stuff, like if you have multiple disks in your system, it's able to do things like, okay, well, one of these disks is an SSD, and so I should use this for fast storage, and then this other disk is a spinning hard drive, and so I should use this for long-term archival of stuff. And it's able to know about these disks and kind of use them all together as one single thing that you see as a user, but the operating system is able to take this data and shove it across these different devices. ZFS is a file system that is more broadly applicable. So APFS is pretty much limited to you having a Mac. You're the people that can use APFS, but I've got a Linux machine and we've got Windows machines here. Nobody else is going to be able to use APFS. ZFS is a file system that comes from an operating system that was called Solaris. This came from a company called Sun Microsystems, which is the group of people that made Java, which I believe you are all familiar with. Yes, yeah. So they made, you're not familiar with Java? Yeah, okay, you're familiar with Java. Sun Microsystems made Java, but they also did a bunch of other stuff, like making operating systems and workstations. ZFS came out of Solaris and Sun Microsystems, and then Oracle bought Sun Microsystems, and they continued developing ZFS, but ZFS behaves similarly to APFS in that it will take a bunch of disks and it will show you one drive, and you'll be able to interact with that one drive, and it will do cool things like, I want to have checksums on all my data. I want to know that when I save it and then retrieve it again later, the data is still the same as what it was before. Or if I have multiple disks, I want to make sure that the data gets spread across all of my disks as opposed to just being put onto one. So if one of my drives fails, then I'm not actually going to lose all of my data. I'm just going to lose maybe some of my data, depending on the configuration of it. BetterFS is a Linux-specific file system that's like an answer to ZFS. ZFS is encumbered by patents. Oracle owns the copyright to this software. There are ways to get it on a Linux system, but generally people have philosophical reasons to not want to run code that's not free and open source on their system if they're running a Linux system. So BetterFS tries to do a lot of the same things that ZFS is able to do, but free and open source. And so my question to you is, why are there so many different file systems? Take 30 seconds to think about this. I'll let you read this XKCD if you want to as well. But this is also a link on the course webpage if you want to check it out later. And I'm going to pop open a survey. So why are there so many different kinds of file systems? I've listed like 6, but like there are there are many more than what I have described here. Data structure overhead. Yeah, I like that. So one of the things that you might have noticed over the last 50 years, I mean, 20 years, I guess? You're all older than 20, right? Yes? Yeah, okay, so in the last 20 years, you've noticed that computers have gotten faster. They've gotten a lot faster. What was your first operating system? Windows 95, okay. That seems a little anachronistic for someone like you. Windows XP? Second one, okay. Windows 7? You can, oh gosh, Windows 8? Windows Vista? Oh yeah, Vista. I've already tried to forget about that, yeah. Computers have gotten a lot faster, and data structure overhead. So yeah, like as computers are getting faster, data structures are gonna, like their performance characteristics are going to change as our processors get faster. Where it may not have been okay for us to use certain data structures in 1987, it's actually okay for us to use them now when we have these multi-gigahertz processors that have many, many cores attached to them as opposed to this one 8 megahertz processor. One tries to fix the flaws of the other and has to compromise? Absolutely. This is what I would like to politely say is the, well, fuck that, I'm going to do it my own way approach. Yeah, I don't like the way that this looks. I think that it doesn't quite work for the thing that I wanted to do. So I'm just going to make my own that is designed specifically for that thing that I want to do. This one, people are selfish and they don't want to share, I think is attached very closely to that idea. Different operating systems and architectures, yeah, so different operating systems for sure. Different architectures, a little bit, only a little bit. The code that's used on Mac OS for APFS, for example, works just as well on Apple Silicon as it does on Intel Macs. It's going to work the same effectively on both of those things because the disk underneath the system doesn't really rely on the architecture of the system. But different operating systems, I can't trivially rip out APFS from Mac OS and stick it on my Linux computer. There's no straightforward way for me to do something like that. Different kinds of file systems for different kinds of machines. So yeah, definitely related to this idea of machines get faster over time. Different needs and priorities that devs assume from end users. I'm going to stick specifically on this idea of different needs and priorities that devs assume, but really specifically different needs and priorities. So, and then many different use cases, yeah. I'm going to use a word to describe this idea that is called workload. The workload really defines how your file system needs to behave. If your data is ephemeral, and so what I mean by that is like these are a lot of temporary outputs from files that are sort of important, but you can reproduce them if you have enough time. You don't really care too much about them. They're all really small. You just want them to come back eventually, maybe. The needs of that are very different from, these are photos of my children that I cannot make again. I do not want to lose these files. And losing them would be catastrophic for me as a person who has this other kind of workload that I'm thinking about here. Systems evolve and the requirements for handling files change, different file types for high-level data types. Yes, we can't have nice things and people build their own file system. Yeah, I like that too. So we've got pretty much everything that I was thinking about here. Different file system implementations for different kinds of hardware, different kinds of workloads, different operating systems, different kinds of data structures, and gee, I wonder if I could make my own. I wonder if I could make my own or this one doesn't work for me. Okay, so this is awesome. Thank you for participating in this. What I'd like to do now is just do a little bit of a reassessment of the textbook chapters before we start talking about vsfs. I want to know how much time I should spend thinking about different parts of this diagram that I'm going to build. So if you haven't joined, please join up now. And I'm going to go to the next slide. And I'll give you 10 more seconds to connect. And I'm going to start it up. Oh, no. Press enter to start the quiz. Okay. All right, awesome. So yeah, an inode is metadata about a file. I'm going to show you an example of some of the kinds of metadata. You've seen examples of some of the kinds of metadata, but I want to look at my own actual file system and think about what kinds of metadata might be in an inode. So that's awesome. Here's the next question. All right, okay. This is there's a best answer here. There's a best answer here. Let me think about each of these. And I do want to hear from you because apparently lots of you think something differently than what I've written here. So I do want to hear from you about what you're thinking about this. The inode bitmap is our allocation structure. And each one of the bits, and we'll look at this in a second, each one of the bits in this allocation structure says this inode is currently used or it is not used. So it's either set as a 1 or not set as a 0. And that says this inode is currently in use versus not in use. The table itself is where all the metadata goes. So if an inode is metadata about files, then the inode table contains all the metadata about the files. That's where I'm going with this. I'm almost never going to ask multiple choice questions on actual tests. So just to make sure that we're not like worried too much about me being really picky about what I'm thinking about here. When I'm thinking about bitmap as data versus table metadata, when I'm using the word data, what I'm describing to me is the actual contents of files. So like this is, if I'm writing my Hello World program, this is the actual ASCII source code for Hello World. This is what data is to me. Metadata, again, is going to be about it. And that half of it is true here. That half of it is true. But the data part for me is the stuff that's actually inside of my files. Can I hear from you? What did you interpret this to mean? Where there's no wrong answer.
It was, I just kind of forgot what the bitmap was for.
Okay.
The used or unused.
Okay.
But also lots of readmes trying to answer quickly.
Yeah, okay, so the question was too fast. I will take that feedback and I'll try to change these numbers next time to be like 25 seconds as opposed to 20 seconds. All right. That's fair. Mixing the two up, that's super fair. Too fast, that's also super fair. I'm going to go to the next question, and then we will take a look at this idea of these allocation structures. All right, okay. So there's a best answer here. Superblock is best block, I think, is the objectively correct answer. And I'm sorry to the one person that answered that I put a red X over top of it. The first block of a file, when we're talking about blocks in general, specifically the superblock is going to be something that's at the file system level as opposed to the data that we're putting into a file. The first block of a file system, that one is a really convincing answer to try to pick. That is super convincing to try to pick. And in terms of vsfs, it's coincidentally true. It's a coincidence that it's true. But our superblock could technically be anywhere in the file system. It doesn't necessarily have to be the very first block. It makes a lot of sense for it to be the first block, but it doesn't necessarily have to be there. Metadata about allocation structures. This one is technically true, but it's not the best answer. It's technically true because a superblock could say the allocation structures are here. And that is metadata about these allocation structures. But it's not the best answer. The superblock in general is metadata about the file system. So the entire thing. This is where we keep a lot of information about how I should work with this file system, what kind of file system is, and a bunch of properties that I'm able to set when I create this file system. All right. That barefoot Contessa is just following me around. Dragonite is here too. I like that. All right. Here's the last question. And this one is me kind of being really picky about stuff in the book. Okay, good. So lots of people saw this. Good. Lots of people saw this. This was kind of a little aside where it's talking about the idea of how a text editor could make atomic changes to your file. So you're making changes to it, you're editing it. Writing it might not be an atomic operation because it could span many blocks of information. If you're like, I don't know, sitting for 30 hours just typing and typing and typing and typing megabytes and megabytes of data. Renaming the file is I can write all this stuff out and then I can rename it. And the rename itself is an atomic operation. And this is getting back to this idea of how file names are kept in our file system. The file names that we have are not actually part of the metadata for the file, which it sounds super, super weird to me. This idea of file names not being in the inode structure just doesn't make any sense to me. But in terms of how our directory structure is laid out and like how we're putting this stuff in the file system, the name of the file goes in the directory that it happens to be in. And so renaming this is, I'm going to change out one of these things at a time. I'm going to change out one of these entries in the directory that I have right now, as opposed to having to do lots and lots of extra stuff. All right. Congratulations to Sakura. Congrats, congrats. Yeah, yeah. Atomic, that's a great question. Atomic here means it either happens or it doesn't happen. It can't be partially done. So you will either be able to rename a file or you will not rename the file. You can't halfway change the characters in that thing, but not the rest of them. With writing, if I take a whole file and I write it out, I might be able to write only half of the file. And then the rest of it gets cut off because my system suddenly shut down in the middle of a write operation. Yes, in the event of an error. So you can guarantee that this thing either happens or does not happen, but it's not going to be in this half-complete state. Yeah. Any other questions about this? All right, okay. So what I'd like to do is I'd like to spend a little bit of time taking a look at this diagram from our textbook. So this is that super high level overview of what, the structure of the vsfs file system looks like. At the very top here, what we have is like the overview of the disk structure itself. So at the very top, we've got the super block that kind of coincidentally happens to be the very first block in our file system. But again, it's a coincidence, and this isn't universally true for all of the the operating systems that, or file systems that we're going to take a look at. But our super block here is, this is metadata about our file system. The kinds of metadata that we can have in our super block is information that's necessary for us to be able to work with the file system. So one example of that is going to be something like the label for the file system, a human readable label. So when I plug a USB drive into my system, it frequently comes up saying something like no name, or unknown disk, or I don't know, movies with a Z on it, something like that. That's part of the metadata for the file system that we're going to have on that disk itself. Another thing that we're going to have as metadata here is going to be the block size. The block size is important for us to be able to know how big, usually in kilobytes, but often in bytes, how big each one of these things are. So the block size is going to say there's 4 kilobytes in every one of these things. Our whole file system is broken up into this structure of blocks. Each block is going to have a different purpose, but at a really high level, we can just think of this as, this is a giant array, and each entry in the array is 4 kilobytes in size, or whatever the block size happens to be. So my super block has metadata about the file system that's going to help me be able to do stuff with the file system. So interpret where to find data and how to work with the file system itself. The allocation structures, so these, no, I don't want to erase. The allocation structures here these are bitmaps. Bitmaps for us frequently is like Microsoft Paint, and it's not actually really far off from that idea. With Microsoft Paint, when we think about a bitmap, and when we're thinking about bitmaps that are like black and white pictures, we're literally thinking of this pixel is either on or it's off. It's either 0 or 1. Pixel 10 is either on or off. It's black or white. The allocation structures that we have here are bitmaps. The bitmap structure that we've got is within this block. It's kind of like another array, except now we're thinking about this as an array of individual bits. So my Inode bitmap is going to kind of look something like this. And then off the end here, and at each position here, 0, 1, 2, 3, 4, we're either going to have a 0 or a 1. A 1 here says that this block, this inode, is used. This is to say that if I look at the second entry in my inode table, I will find an inode. If I have a 0 here, this says, if I look at the third entry in my inode table, it is not used. So this bitmap is here to basically say there is an inode here or there is not an inode here. The inode bitmap itself is referring to the table of inodes. And my table of inodes is like a big chunk of structures. So there's like structs that I've put inside of this table that represent each one of the files that I've got. I'm going to come back to this in just a second. But what I want to do is go back to my terminal, and I want to make this a little bit bigger. And I'm going to zoom in here. And I want to start thinking about the kinds of metadata that might actually be in an inode. So I'm going to do ls, and I'm going to do ls with this new option called L. L stands for long output. I want to see more information than just the names of the files that I've got in this directory structure. The metadata that we have for a file consists of a bunch of different things. At the beginning here, what I'm going to do is I'm going to take a screenshot of this, and I'm going to put it inside of that file and mark it up. There we go. So our inode structure here, I'm going to just draw a little arrow here that kind of indicates that we're zooming into this thing right now. We're zooming into one of these inodes. And it refers to an individual file that I've got in my file system. The metadata that we have here is going to be things like permissions. The system that I'm running right now is, it's used by me. It's used by me and not really anybody else. But there are still permissions attached to this system because there can be multiple users that are attached to it. This is really important when we get to things like thinking about aviary, where there's lots of people connecting to the same system. But there's permissions here. The first block of permissions here is going to be for the user themselves. So this is going to be of the form RWX, read, write, and execute. The second structure here, this is going to be for something that's called the group. And this will also be read, write, or execute. And then the last part here is basically saying everybody else. In Unix and Linux, this is something that's called other or world. And it's also read, write, and execute. And so what that means is that for this particular file, me, F. Bristow, the owner of this file, has permission to read and write readme.pdf. The group that I happen to be in here is also this, but if you're connecting to Aviary, you're going to see stuff like CS under G. In my case, I still see CS grad because I guess I'm just forever a grad student here. That's our group structure. And when we're in a group, we'll have certain permissions on files that are attached to that group permission. This part here refers to the file size. This says how many bytes are currently in this file. This is metadata about when it was last modified. And then this is metadata, again, that is not actually stored in the inode. The name is not actually stored in the inode. We're going to come back to this. I will post this document in its current state up on the course webpage for today's lecture, but we will come back to this on Wednesday and finish up thinking about how this overall structure looks. So what you should be able to do at this point is describe how an operating system manages processes. You should start to be able to describe some of the data structures that are used to represent files and directories in Unix. You should start to be able to describe how a specific file system is implemented. And we didn't really talk about this one at all. You should at some point be able to show how common file operations are performed in terms of manipulating a file system's data structures. That's it for today. Thank you all for coming out, and I will see you on Wednesday. Bye, everybody.